Equilibrium is not just a useful idea for finding reactions of bodies that keep them in static equilibrium. It's also very useful for finding geometric properties, or as an analogy to finding geometric properties such as centroids. In a typical kind of context here, you see in this photograph is what we call a concrete tilt-up panel. That this concrete segment is cast on its side. You see sort of the edge of that right here, and that cast on its side, and then they are lifted into place. And in that lifting operation, certainly one of the key aspects of that is finding out where the center of mass is, so that we understand what's going on with the crane as it's lifting this particular panel up. And so the centroid is really, from an analogy standpoint, is right where the tipping point is on this thing. Now, if we could balance the object at just the right point, it wouldn't teeter-totter at all and just be a perfect location. Right? And so that's the tipping analogy aspect of things. And so when we go to do the kind of calculation, now oftentimes what we're working with are nice geometric areas from which we can do what we call the composite approach, as opposed to an integral approach. And the key there is to think about positive areas and negative areas. So notice that they're lifting this panel is actually looks like two panels together. It actually was cast as one. There's just a line of symmetry here that's going on at work. And so I'm just going to use one half of the area to show what I call the positive area. It's really the whole thing here. But that's the positive area, and I'll call that area 1. That's all this gray area, and then we've got two of these other holes that we'll call 2 and 3. These are rectangular holes. And so when we do this tipping analogy, the way that we can think about this is that really from a sum of moments kind of perspective, that here's this reaction that we're talking about, and we've got for area 1 this whole thing, and the way I've shown it now, we've really got two of those, and its balance point is somewhere right in here, right? So that would be area, or the weight of 1, or the area of 1, and its moment arm with respect to a datum, which I've chosen to be the base of this thing. That's our distance, y sub 1, going up to that one, right? And then we'll subtract off, in effect, the areas of these holes. So what would be weight 2, or area 2 and area 3, they have distances to their centroids, y2 and y3. And so the way we handle that in a tabular kind of approach is that y1 would be a positive, as would y2 and y3, but the areas for that positive area for area 1 would be positive, but the area number 2 would be negative areas. And you can kind of see that here if we were to sum moments about our datum, that let's take the way I've got it drawn here as G. We've got, let's take clockwise as positive, so we'd have positive W1 times Y1, and then minus W2 times Y2 minus W3 times Y3. See, these are first moments of the area, and then of course I've got my reaction here, right? So that would be our total weight, and that's going also in the opposite direction, and it has its location at y bar, our actual location that we're interested in, set it equal to 0, and you're going to end up with then that GW times y bar is equal to W1 Y1 minus W2 Y2 minus W3 times Y3. And there you say, well, that's weights, that's how I find a center of mass, but what about this idea of center of area? And so notice that these weights are just equal to a unit area times, or sorry, the unit weight times the specific area of that object, right? And so the gammas would be all the same, they'd all cross off, and so we'd have our total area y times y bar would be equal to a1 times y1 minus a2 times y2 minus a3 times y3. In other words, sum of all the ai, yi, if we're letting the area itself now become negative, divided by then that total area, is what's going to give us our centroidal distance. I note again that, I sort of did a little flip-floppy on you here. I said, well, a negative area, well, you don't calculate it as a negative number, you just go find out what that base times that height is for that specific area, you pop it down here, and it becomes a minus sign. If in the tabular method, that's where you put the minus sign. If you're going to actually write out an equilibrium equation, then you could choose to insert it, count all the areas as positive, but then choose to insert the negative signs as you're careful and your attentiveness to how you're handling your math up here, or your free body diagram, so to speak, for those areas.